Hi viewers, welcome to all. Here we are discuss about a project, power efficient approximate divider architecture for error resilient applications. Okay, the three approximation divisions that are shown in the study are employing an array based architectures. As a result, it's able to accomplish considerable hardware saving while maintaining a high degree of accuracy in comparisons to other contemporary approximation design. The divider in these applications has complicated circuitry which results in higher delay between the various computing blocks and increases the amount of power consumptions. Therefore, coming up with an approximations of the division model would result in design that were far more power efficient. Okay, so in this research we propose a novel algorithms called approximation subtraction, that is AxSUB. Okay, so with the goal of reducing the complexity of the hardware while still obtaining accuracy within the allowable bounds of the algorithm. In order to demonstrate the usefulness of the AxSUB, okay, that is the approximate subtractions, both the proposed approximate subtractions and current approximate subtractions units are included into the restoring array division, that is RAD. Okay, architecture. The effectiveness of the proposed designs of AxSUB 8 by 4 and the AxSUB 16 by 8 was shown in the paper. Okay, we have proposed the XRMDZ 8 by 4 designs. Okay, that is a XOR multiplexer divider cell. Okay, so which was suggested improve the accuracy of the column wise functions, while but the XRMDZ 16 by 8 designs uses a number of rows with the correct architectural functions. In addition, the trade-off between the accuracy and the high performance for various approximation divisions in explored in order to determine which designs achieves the best compromise. So this is done in order to find which designs provides the best possible outcomes. This is done in order to determine which designs strike the optimal balance between the two complement elements. Okay, so this proposed architectures was created using a Verla HDL and synthesized with Xilinx Vertex 5 FPGA, and all the parameters were studied and compared with respect to area, latency and power. Now we can verify the base paper. So this base paper we have designed the three different architectures. One is the exact method, another one is the AxSUB. Okay, that is a approximate subtractions. Okay, it depends upon restoring array division. Okay, and the proposed method we have designed using the XOR multiplexer divider cell. Okay, so here the paper they are given, this is the exact design. Okay, so 1 bit full subtractor cell. Okay, so with support of restoring array division. Okay, so this is the existing architecture, that is the exact method. Okay, so here they are given a AxSUB. So this is a subtractor cell, but we have used this cell into this architecture. This is a approximate full adder cell. Okay, that is a AFS. Okay, so this AFS only they will called here. Okay, so this is the proposed 8x4 RAD AxSUB design. Okay, so here the LSB part only they are used this AFS to reduce the complexity, and we will create a approximate in the exact design. Okay, so we have proposed this architecture with the help of XRMDZ divider cell to reduce the logic size complexity and to increase the more accuracy in this architecture. Okay, so here we can verify the coding part. So this is a top model for AFS 8 by 4 divider cell. Okay, so here we have used 8 by 4 means 8 7 down to 0 is a dividend and 3 down to 0 is a divisor and quotient and remainder. Okay, so here as per the architecture the AFS divider cell will be used in the first cell. After that we have used a XOR divider cell. Okay, so this level of simulations we have present here. Okay, so here, so this is a simulation for approximate subtraction divider cell 8 by 4 architecture. Okay, so here you can check the dividend and the divisor. Okay, the same method we have developed in the ExOR-MDC. So this is a ExOR-MDC divided cell architecture. So here we have solved some of the errors in the existing architecture. So here you can check the all the bits. Okay, so here this is the error line. Okay, so here you can check. So this is the exact method. Okay, but this is the approximate method. Okay, so here you can check 102 divided by 7, it will produce a 15 by 7. Okay, quotient equal to 15 and remainder equal to 7. But here you can check the quotient equal to 14 and remainder equal to 4. Okay, but in some cases the error will be produced in the exact method. Why? Because we are checking the check data equal to 7 down to 0, but the dividend equal to here dividend equal to 7 down to 0, but divisor equal to 3 down to 4. So as per the architecture we are taken the quotient equal to 3 down to 0 only. Okay, not 7 down to 0. So it will be truncated. Okay, the truncated balance output only produced in the output of coefficient and remainder. Okay, so here we have designed this architecture in 16 by 8. So this is a 16 by 8 architecture. So this 16 by 8 having reference paper. So this is the architecture for 16 by 8 proposed design AxSUB M2. Okay, so P equal to 4. Okay, so as per this design architectures we have developed our architecture, that is a exact method and approximate subtraction divided cell and ExOR-MDC method. Okay, the three different architectures we have developed it. Okay, so here the SOD and DLOD and ARL architectures they are given. So here this LOD means it's a leading one detector. So leading one detector we need to find from the S bit and D bit. This output we have shown here. Okay, so this is a 16 by 8 architecture. Here you can check dividend equal to 16 and divisor equal to 8 and quotient you can check and with the check data. Okay, so here you can check the quotient 7 down to 0 and check data with 15 down to 0. You can check the all outputs. Okay, and this all method we have synthesized in Xilinx Vertex 5 FPGA. Okay, we have designed all the comparisons of the coding. Okay, so here total comparison is 1 2 3 4 5 6 comparisons we have designed. Okay, so 8 by 4 we are given for 3 architecture and 16 by 8 we are given for 3 architecture. Okay, but in a video file we can't possible to show all the things. Okay, yeah, this is a AFS 8 by 4 divider cell. 8 by 4. Okay, so here you can check the parameters as slice LUTs and occupied slices and the IO base. Okay, and synthesize you can check delay. Okay, so 18.259 and you can check the RTL schematic for AFS. Okay, so in this AFS architecture we need to use two divider cell. One is a AFS, another one is a exact divider cell. Okay, so this is a AFS divider cell architecture, AX subtractor and a multiplexer, and this is a exact divider cell. Okay, full adder and a multiplexer. Okay, and the final divider cell and the output we are taken here. Okay, so this is a remainder output 3 down to 0 and quotient output. Okay, so this is the RTL schematic. Next, the proposed one is ExOR-MDC. So this is a ExOR-MDC architecture. So here you can check the slice LUTs and occupied slices and number of IO base. Okay, and you can check delay. So here delay will be 11.430 nanoseconds. Okay, here delay will be reduced and logic size is also reduced in the compared to the AFS architecture. Okay, so here you can check the RTL schematic. Okay, so this is ExOR-MDC divider cell. So here as per the architectures we have created a novelty design. Okay, so here ExOR-MDC divider cell output we are taken here. Okay, and so this is a 16-bit architecture. Okay, ExOR-MDC 16 by 8 architecture. You can check all the parameters here. You can check the RTL schematic 16 by 8 divider cell. Okay, so in this 16 by 8 divider cell already told you, we are used the SLOD and DLOD and finally covered with the ARL architecture. Okay, so this is a leading one detector. Okay, so this is all the divider cells in the XRMDC. Okay, so here we are compared, and we'll put a comparison document for this project. This is a comparisons document. Here you can check it. Okay, the 3 comparisons for 8x4 and 3 comparison for 16x8. Okay, so this is a comparisons analysis chart. Okay, the next thing is we have written an abstract document for this project. Here you can check the base paper abstract, improvement of the project, proposed title, proposed abstract, existing system, and related notes. Okay, and proposed systems with truth tables, and introduction to VLSI design. Okay, so all the notes we are given here with the literature survey, and finally references. Okay, thank you.
If you need more video related to VLSI project, please like and subscribe this channel.